Dear students, I, Professor Prashant Bhuva, Dr. Subhash Technical Campus, Junagadh. Today's in this video, we will discuss about wind load calculation, subject, design of steel structure, and it should be considered in chapter design of industrial building. So, we all of you know that at any building, we will calculate mainly dead load, live load, earthquake load and wind load. So there are all different codal provision are there. But in wind load, we specially calculate when the building is high rise. So today in this video session, we will discuss about effect of a wind load on buildings and how we calculate with the codal provision of IS 875 part 3. So wind, the wind is moving mass of air. Buildings and other structure represent obstacle that deflect in to the wind. So covering the kinematic energy of moving air mass into the potential energy of pressure. So the wind loads result from the force extended by kinematic energy of moving mass of air, which can produce the combination of direct pressure or it may be a negative pressure or suction, and drag force on building and other obstacle it's in path. So the wind force are typically assumed to be applied normal. It may be a perpendicular to the affected on surface of building. So the wind pressure increase as a function of wind velocity, and the average mean wind velocity of any particular area or measure over the long period of time generally increase with the height. So depending on that wind pressure velocity located at particular area, we should be kept in mind what should be our building height, and beyond that height what should be the criteria to resist this wind pressure. So the rate of increase of mean velocities also function of ground roughness, and it should be interference offered by surrounding objects including other building, vegetations and landforms. So you can see that figure, that wind pressure, it may be a laterally perpendicular to the building at any form, and wind should be affected. So it should be a wind pressure converted after the kinematic velocity. So next you can see that wind face direct pressure building surface perpendicular to the winds and walls receive the major portion of and force from the direct pressure. If wind direction you can see in this figure, so it should be a directly pressure to the wall of our building surface and it should be the affected, and drag force also should be act. So these are the different kinds of pressure should be directly proportional to the building and it should be affect our design criteria also. Now load acting on high rise building, that we know this, for the vertical load we segregate dead loads and live load, and for the lateral loads and very important loads are earthquake loads and wind loads. So both load are laterally on building and it should be a severe effect if we not considering the good criteria to the pressure of this lateral load on building. So the variation of wind velocity with height, what should be the change if height and velocity should be occurs. So the variation of wind velocity with height near the earth's surface, the motion is opposed and the wind speed reduced by the surface friction. At the surface and the wind speed reduced to zero, and the beginning of increase with the height. At the some height, we know that gradient heights, then motion may be considered to be free on the earth's frictional influence and will attain its gradual velocity. The gradient height of 300 meters for flat ground and 550 meter for very rough terrain. So what should be our terrain category and what should be our building height? You can see the different three shape in our figure. One is shear, moment and deflection. So these three are affected in a building when the wind load of tall structure are affected. So likewise, what should be our terrain category, what should be our gradient heights and what should be the topography. According to that, we design or shape our building as well as height and width criteria to resist this wind force. So the wind effects on structure can be classified as static and dynamic. So in static wind effect primarily cause elastic bending and next and very severe effect of twisting of structure. So it should be prevented to our building because twisting moment we all know that's very dangerous, and when that height should be higher, there should be more severe effect on building. So the dynamic for tall and long span, the slender structures, a dynamic analysis of structure is essential. The wind cause fluctuate force on the structure which includes large dynamic motion including oscillation. So we know that the dynamic side it's very preventable and we should be calculate very essential while our building in a earthquake zone. Then separately dynamic analysis should be done before we construct the high-rise building also. So likewise wind is also affect because it should be the fluctuate force. It's not constant throughout the building are same. So this is the rigid frame structure. You can see the number of span versus feet diagrams. So it should be a different in rigid frame structures. Now design wind speed. So the design wind speed is denoted by Vz and it should be Vb into K1, K2, K3. So the Vz is design speed, wind speed at any height in Z in meter per second. K1 is probability factor 1.06 for importance building of life 100 year. K2 is terrain categories, K3 is topography factor, and after that design wind pressure Pz. Pz is denoted as 0.6 times Vz, where Vz is Newton per meter square. So the wind load calculation, wind force F is equal to A into Pd into Cf. For that we calculate the ratio of A by B, H by B and Cf using the graph. So the F is wind load, Cf is force coefficient, Pd is a design wind pressure and A is a effective frontal area obstacle wind with the identify each structures. So these are the step. For that we have calculate finally wind load F and it should be affected on these following parameters. So these are the graph is given in IS 875 or you can say figure 6 in IS 875. So it should be the different CF value is depend on elevation and plan. According to that ratio we have calculate the CF value for the versus of ratio of A by B and H by B. You can see in this figure. These are the two graphs are given in figure number 6 in our IS 875 part 3. So now calculating the wind load at different height. It should be a different height. We have to calculate wind load 10, 50, 20, 30 and floor level using static method with help of given data. So start with the one numerical example. So we can clear about the what are the steps to finding out the wind load as per IS 875 part 3. So in our data number of story are 10. Height of each story is 3 meter. Height of the structure, so it's of course 30 meters. Location of building are in Vadodara. Design life of structure 15 year. Category 3. Topography plain with upwind slope less than 3 degree. So these are the data is given. So you can see this plan. So plan is given 24 by 15 meters and one bay should be 6 by 5. So like that the 15 meters the width is given and 30 meters totally height. So elevation and plan you have to draw roughly. So you can idealize that plan to width ratio and height to width ratio of our given data. Step 1. Calculating the design wind speed. So design wind speed is denoted by Vz and is given in IS 875 part 3 page number 8. Vz is design wind speed at height Z. So it that VB is equal to basic wind speed at any height. K1 is probability factor, and it's given our IS 875 page number 11 for K1. For K2 is terrain height structure size factor, and it's given page number 12 in IS 875 part 3. K3 is given in clause number 5.3.3.1 page number 12 in IS 875 part 3. So basic wind speed, first of all we calculate value of VB. So value of VB is given as per IS 875 part 3 clause number 5.2. So in our case our building is located at Vadodara. For Vadodara VB value, it means basic wind speed is 44 meter per second according to given data. So we will take VB is equal to 44. Next K1, it means our probability factor. So K1, or you can say the risk coefficient, the value of K1 depends upon the probable design life structure and basic wind speed VB. So already VB is given. So first of all K1 is given at table number 1 clause number 5.3.1 IS 87 part 3. So in our case our VB is 44. You can see in table number 1 in horizontal that wind speed is given to you and vertical class of structure is given and the mean probable design life. So in our case our mean probable life is 15, all general building and structures. So for 15 life year our VB is 44. So our K1 is 1 according to our data. Next K2. K2 is nothing but terrain category heights of structure is given in IS 875 part 3 table 2 clause number 5.3.2.2. So there are the three class given in our IS 800, class A, class B and class C. So if the class is not given, so you have to decide it according to height. You can see class A, the structure of their components such as cladding and glazing, roofing, etc. having maximum dimension less than 20. If any dimension greater horizontal or vertical should be less than 20 meter, then it should be considered class A. That dimension between 20 to 15 meters, it should be a class B, and that dimension should be greater than 50, then automatically it should be a class C. So in our according to data, our height of building is 30 meters and width is also 30 meters. So in our building it should be considering class B. So for that you can see that different height we calculating the wind load, because at every height should be the intent should be of wind load should be varies. So at 10 meter, 50 meter, 20 meter and 30 meter. According to that our category is 3. So K2 will be calculated according to height. So for 10 meter it should be 0.88, from 15 meter it should be 0.44, 20 meter 0.98 and 30 meter 1.02. So you can see that value of K2 given in table number 2 clause number 5.3.2. Here our category is 3 and class of building is B. So for different height we have to calculating the K2 for 10 meter, 50 meter, 20 meter and 30 meter. You can see in this table of 2. This is our height is of building. These 4 category of building are given, and in that below the different class A, B, C are given for table number 2. Now we calculate K3. It's very important because it's the topography factor. So according to clause number 5.3.3.1, the effect of topography will be significant at site when the upwind slope is greater than 3 degree. Then and then it should be calculated. Otherwise, below that, the K3 may be taken is equal to 1. So it means our upwind slope less than 3 degree, it should be taken as 1, or slope greater than 3 degree, the method of evaluating the value of KB value greater than 1, and it's given in appendix C of our IS 875 part 3. So upwind slope, so in the degree is less than 3, then in our according to our data the K3 should be 1. So according to our data we have to take K3 is equal to 1, but in the different data or different terrain category upwind slope, it may be a varies. So now we calculate design wind speed Vz, Vb we have calculate according to our table, K1, K2, K3 we already calculate. So our Vz at different height we calculate. So at 10 meter height, what should be the change? Our K2, K3 is 1, K1 is 1, only the variable is K2 with the variable of height. So you can see the right hand side table. At 10 meter our Vz value is 38.72. Likewise at 30 meter it should be a 45.32 because our K2 is varies. Now after calculating the Vz, our next step to calculating the design wind pressure. So calculating the design wind pressure, Pz is equal to 0.6 times Vz. So Vz we already calculate, multiply by 0.6. That equation of Pz is given in clause number 5.4 IS 875 part 3. So you can see that just multiplying by 0.6 in our previous table at different height of 10, 50, 20, 30. We will calculate Pz value Newton per meter square. In right hand side you can see in our table. So 10 meter 899 and as a 30 meter it should be a 1232. Now our next step to calculating the design wind load. So design wind load is calculated as denoted by F, AE into PD into CF. So what should be the F? F is nothing but wind load. AE means effective front end area obstructing to the wind and which is identified for the its surface. CF is force coefficient. Again PD we already calculate design wind pressure. So that wind load F we calculating. So for that, first of all we finding the value of CF using figure number 6. So as per IS 875 part 3 clause number 4 5.2, first of all find H by B ratio and check it's greater than or less than 1. So help to decide with the graph to find the CF. So if H by B value is greater than or equal to 1, then use graph 6a. If your H by B value is less than 1, then use class 6b. So our height is 30 meter, our length is 24 and our breadth or width is 15. So first we calculate A by B ratio is 0.62, H by D ratio is 1.22. So our value should be greater than 1. So we have to use graph 6a. So figure 6, there are the two graph is given in IS 875 part 3, 6a and 6b. 6a for H by B greater than value 1, 6b for H by B value less than 1. So in our given data we should use graph 6a. So now you can see the graph 6a for H by B greater than of 1. So in horizontal A by B ratio is given. So our A by B ratio, you can see in previous slide it should be 0.62 and our H by B ratio 1.25. So in horizontally we located, you can see in our figure it should be located for the red line 0.62 and our CF we have to calculate. So our H by B is 1.25, so it should be below 1 meter graph of vertical, you can see as a red portion. Now both H by B and A by B are touched in a parallel to the vertical side, CF value is given. So you can see that our location point of in between 1 to 1.5, it's not a middle, so we will take CF is equal to 1.2. You can see in this figure our point located, both the point bisects at the mid height of 1 and 1.4. So we will take CF is equal to 1.2 according to 6F. Now we calculating the frontal area A. So A is the effective frontal area. Here we can calculate load per unit area. Therefore frontal area is 1 by 6. It means shortest span between column. So A is 1 into 6. It means 6 meter square. How we calculate? You can see the plan. It should be shortest span 6 meter and 1 meter as a strip. So it should be 1 by 6 meter square, and it should be the wind direction of frontal where the building is located. So now calculating the value of design load at different height. So we make one table: height, PZ, F, and wind force F in kilonewton into meter, because we have to calculate F in Newton per meter. So at a different height, we already calculate PZ. Just multiply by A into CF. Our CF value is 1.2. A we calculate 6 meter square, and PZ already given. So according to that equation of F, our F is Newton per meter converted into the kilonewton per meter. So you can see in right hand side column of our table. So at 0 to 10 meter, our wind load is 6.58 kilonewton per meter, 10 to 5 7.5, and 20 to 30 9.02. So you can see the effect of height to the wind force in this table. When the height it should be rise, our wind load should be increase. So this is the wind diagram. You can see at 0 to 10 meter it should be 6.58, 10 to 15 it should be 7.513, 15 to 20 8.166, and 20 to 30 9.02. So you must be draw after calculating the wind force diagram. After that you have to calculate force at each story. So make the table story number. In that descending order you have to start. It means story 10, 9, 8 to 1. The loading level, it means our 3 meter story level are given. So 27 to 30. Likewise 27 to 24, like 3 to 0. So the story height is uniform. You can see in our third column it should be a 3 meter. So the design force you should be calculate. So how we calculate? So up to 10 meter, it means our 1, 2, 3 story are same, because 0 to 10 the value should be 6.5. After that you get the interpolation 10 to between 12. So its the value is 7.13, 12 to 15 7.5i, 15 to 18 7.90, 80 to 20 8.20, 21 to 24 8.9, and finally 27 to 30 9.0. So force at each story. So design force multiply by height. So finally we force at each story in kilonewton. So 10 story 27.06, in first story 19.74. You can see up to 10 meters there are no effect in a force of each story. It should be constant 90.75. When our height should be rise below 10 meter, it should be very gradually 21.39, 22.53, 23.7, 24.75, 25.5, 26.28, and highest 27.06. So you can see that figure, the different story, your force act and each story are different. So likewise we calculate building lump mass of different story height. Now you can see that wind pressure and different story height of our case. So the different height, you can see that 0 to 10 meter our wind force is constant. After then it should be gradually varies. 15 to 20 it should be again varies, and highest it should be 20 to 30. So finally we draw this graph. So these are the one numerical, or you can say the one part of our design industrial building, and it should be asked in 7 mark to calculating the wind force for given data. So thank you for watching this video.